In our next example, example 6, the question reads, if a ball is selected at random from an urn, a vase basically, containing 3 yellow, 4 red, and 2 green balls. So we're going to select a ball at random. What is the probability that the ball will be green? So the probability of picking a green ball. So first of all, let's figure out the size of the sample space, how many balls are in that urn. So we're simply going to add the 3, the 4, and the 2 together, and that's going to give us 9 balls overall in that urn. We need to pick a green one. Well, there were 2 green ones. So the probability of picking a green one is 2 out of the 9 in that urn. I'm going to leave it as a fraction. I know it's already reduced, so we might as well leave it as a fraction. Part B is asking, well, what's the probability of a purple ball? Purple? Well, we still have 9 balls in there, but none of them are purple. So this is what we call an impossible event, and that's 0. So the probability of getting a purple ball is 0 out of 9. It's not a trick question. It's just making sure you understand that that cannot occur, and it makes it impossible. Okay, let's go look at a deck of cards. So example 7, a card is drawn at random from a standard 52 card deck. We want to find the probability that the card drawn is a heart. So part A says the probability of getting a heart. So again, it helps that you know that there are 13 hearts in that deck. That's one suit. That would be ace through king. So ace 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen. And that's 13 out of 52, which is 1 out of 4. What this is really saying is 1 out of every 4 cards is a heart. Part B says, what's the probability that it is a red card? Well, there are 13 hearts. There are also 13 diamonds. Both of those are the red suits. 13 and 13 is 26 out of 52, which reduces to 1 out of 2. So half the deck is red, the other half is black. Part C is asking for the probability that the card drawn is a king. Well, there are 4 kings out of the 52 cards in the deck. That would be 1 out of 13. So 1 out of every 13 cards is a king. And again, that should make some sense because 13 cards make up a suit, and there's 1 king per suit. Part D is asking for a red king. So what's the probability that you're going to get a red king? Well, the red kings would be the king of hearts and the king of diamonds. There's only 2 of those. So that would be 2 out of 52, which is 1 out of 26, or 1 out of half the deck. That is the 26 cards that make up the 2 suits. And finally, part E says the king of hearts. So what's the probability that we get the king of hearts? Well, there's only 1 king of hearts out of the 52 cards that are in our deck. So the probability of getting a king is 1 out of 52. Okay, our next example goes back to a pair of dice. This is example 8. It says a pair of fair dice is rolled. What's the probability that the sum is less than 5? So for part A, we want to find the probability that the sum is less than 5. So that means a sum of 4, a sum of 3, a sum of 2. I'm not going to list a sum of 1 because there's no way to get a sum of 1 when you're tossing a pair of dice. So let's list out what's going on. The only way to get a sum of 2 is to roll a 1 and a 1. The only way to get a sum of 3 is a 1 and a 2 or a 2 and a 1. The ways to get a sum of 4 would be a 1 and a 3 and a 1, or doubles of 2 and 2. So what I've done is literally listed out the ways I can get what we need for this probability event. So when I count them up, I have 1, 2, 3, 4, 5, 6. So all together, there are 6 ways to get a sum that is less than 5. Again, that does not include 5. And now we need our sample space. Well, our sample space, when we toss the die, is going to be 6 times 6. 6 possibilities on the first die, 6 possibilities on the second die to give me 36. So the probability of getting a sum that is less than 5 is 6 out of 36. I'll reduce that. That's 1 out of 6. You can take it to a decimal. I'll use fractions when they're convenient and easier, quicker. Okay, part B says, what's the probability of at least 1 6? Okay. So at least 1 6 means one die is a 6 or both dies are a 6. So I'm going to write that out. One die is a 6 or both are a 6. Now they didn't tell me which of the dies, the first or the second, is the 6. So this one die being a 6 is made up of a 1 6, a 2 6, a 3 6, a 4 6, a 5 6, or a 6 1, a 6 2, a 6 3, a 6 4, or a 6 5. So there are 10 of those. And then both of them are a 6 would simply be the doubles, 6 and 6. So when I count them up, you're going to see that we have 11 out of 36. So again, one die is a 6 does not imply an order. So I had to address the first die being a 6 or the second die being a 6 and just count them up. So, and that's why knowing what the sample spaces are is pretty handy because it makes counting them up fairly easy on us. Okay, so we've done cards, we've done dies. Let's come in and do some coins again. So example 9 says we're going to come in and toss a coin 4 times. So coin toss 4 times. What's the probability that 3 heads and 1 tail are tossed? So the probability of 3 heads, 1 tail. So that would be a head, 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 tail, or we already have done this kind of thing. We know we can rotate that tail through those spots. And sure enough, if I do that, I get 4 of them. So that would be 4 out of, and now we need that sample space. So the sample space would be 2 choices on the first toss, 2 on the second toss, 2 on the third toss, or 2 on the last toss. 2 times 2 times 2 times 2 is 16. So 1/4 of the time, when you toss a coin 4 times, you're going to end up with 3 heads and 1 tail. And again, the order is not implied in any order. Okay, part B is saying, what's the probability that the last toss is a tail? Okay, the sample space isn't changing here. It's still that 16 because we're still tossing it 4 times. Now what they're asking me, here's my 4 tosses. They're saying this guy is a tail no matter what, but they're not saying anything about the first 2, the first 3. So this first toss could be a head or a tail. That makes 2 possibilities there. 2 possibilities on the next one and 2 possibilities on the third one. The last one is the only one we know for sure. So that was 1 possibility. So we end up with 8 possibilities with the last toss as a tail. That's really half of them. So half of them have a last toss as a tail. The other half have the last toss as a head. So when you put it that way, it should help you make a little sense out of that. Okay, part C on that one says the first toss is a tail and the last toss is a tail. So probability first is a tail and the last is a tail. So let's use the same kind of analogy. We know that we're looking at a sample space of 16. I know that this is a tail and this is a tail. So those are only 1 choice apiece. But the middle ones, they didn't ask me about. So I know that there's 2 possibilities on the second toss, 2 possibilities on the third toss. Altogether, that will give me 4 out of the 16 or 1/4. So instead of having to list these out, it was just easier to look at it from a multiplication point of view. Okay, and then finally, let's answer a couple more questions from a distribution. Your book in this section really enjoys the distribution tables. So this is example 10. And what it's listing is in a survey of consumer spending methods conducted in 2006, a while ago now, the following results were obtained. So here was the payment method that people used. So when they paid for something, they paid with a check, which probably doesn't happen very much anymore. And that was 37. Cash was 14. Credit cards was was 25. Debit cards, which got lumped in with ATM cards, was 15. And then other would be 9. So maybe a wire transfer or a cashier's check or something like that. And down here, what you actually have is the transactions. But more importantly, it's a percentage. And because it's a percentage, we know that we can translate that directly over to the probability, because this 37% would be 37 out of 100. So if a transaction tracked in this survey is selected at random, what's the probability that the transaction was paid for with a credit card or a debit card? So we're looking for the probability of a credit or debit. And because that word or is in there, I know that I can add those individual probabilities together. So the credit card was 0.25. The debit card was 0.15. So 0.25 and 0.15 gives me 0.4 or 40%. Okay, part B says, what's the probability that a transaction selected from this survey with cash or some method other than a check, credit card, or debit card? So with cash or some method other. So we want cash and some method other than the debit, the credit, and the check. So we're looking at the cash and the other. So the probability that cash or other, that would be the 14, so 0.14 plus 0.09. It should be 0.23 or 23% of the transactions. And that wraps up our beginning section on probability.